Alright, so in this video we're going to talk about the second fundamental theorem of calculus. Some books don't call it that. Some just kind of say what it is, don't really have it being the second fundamental theorem of calculus. And what it gets at is mainly that the derivative, that's what this is telling you to do, and the antiderivative, that's what this is telling you to do, are basically inverses. So for the most part, they're going to cancel each other out. Now, the only thing that's a little different in the book likes to do things like this, making it from a to x and not x squared. When that's true, it really does just replace it with x. So what's going to happen here is you could take the antiderivative and then take the derivative. But we don't really want to, especially if it was too difficult to actually do. So what we're going to do is we're going to just apply the rule that these are going to cancel out. So all we're going to do is plug in the x squared plus 3x squared, and there's nowhere to plug it in with a 4. Now the problem is the antiderivative undoes all of this part right here. And then you plug in this, and you take the derivative of it. You haven't really done an antiderivative on this for the derivative to cancel it out. So you have to, no matter what, multiply by the derivative of whatever you're plugging in, 2x. Now that's the top, minus the bottom, which would be 4a cubed plus 3a squared minus 4 times the derivative of the bottom, which is 0, because this is an a and we're taking our derivative in terms of x. Now the book doesn't even really talk about the second half because the second half goes to 0, but it's really top minus the bottom. You plug in your bounds and you multiply by the derivative of them. And that's the part that people forget. They want to just cancel out their bounds, but they want to forget to multiply by the derivative. So if we were to clean this up, this would be 8x to the, well, that's 6 and one more makes 7, plus 6x to the 5th minus 8x. Now, if you're in my class and you're doing this on your own, 1, 2, and 3 probably gave you to think that it should have just been this without the 2x, basically. That's what the first three kind of lead you to believe, is that they just cancel out 100%. But you got to multiply it by the derivative. So in this case, you're going to have, you notice that these are y's and these are x's, you still plug them in. So we cosine of 6y plus sine of 4y, and then times 2 minus, well, 0. And that's really it. Derivative of 2y is the 2. Derivative of 8 is the 0. And in 6, you're going to have x plus 2 being plugged in for x, plus 1 times the derivative, which is just 1, or x plus 3. That's really it. So what's the rule exactly? So the rule exactly is, let's say we had, let's make this f of x, f of y. Let's put that as f of y dy. And this is going to be g of x and h of x. And you're taking the derivative in terms of x. Now this is not how the book has this. The book has the derivative from a to x of f of x, f of t, I believe, dt, or some value, and this just equals f of x. You basically plug in the x for the t, and there's no derivatives at all. But the truth of the matter is, you can have the x squared up here, you can have a 2y over here, and I see them all the time, put stuff in there. So what we need is it's going to be f of h of x, whatever this thing is, you plug it in, times the derivative of whatever you just plugged in, h prime of x, minus f of g of x, times the derivative of whatever you plugged in, g prime of x. And then you kind of compute all that, and you've got it. Plug in the top times the derivative of the top. Plug in the bottom times the derivative of the bottom. It's basically the chain rule more than anything else. Alright, so don't really want to do this antiderivative. I mean, if we had to, you probably wanted to take out the 2, do some factoring, and actually kind of cancel down a little bit. But, so see what I mean? Like you take the 2 out, a plus 1, is we over a plus 1 squared, so we can cancel one of those out, and it's the same as the integral of 2 over a plus 1. And we're doing this and taking the derivative of this from x to 5. So this is just going to be 2 over x plus 1 times the derivative of x, which is 1, minus 0. Okay, wasn't too bad. Now, here's a question I got for you. How do you do, and if you're in my class watching this in chapter 4, how in the world do you do this? We have not seen one like that. Later on we'll learn it's a natural log and all that fun stuff, but right now we would be stuck. Alright, how about the cosecant? I don't know if we know that one either. But we don't need to know that one because it is, we're going to be doing the derivative of it. So we plug in 2x times 2 times the derivative of the inside. Alright, well, what about this one? Well, let's see, f of 1 times the derivative of 1, which is 0, minus f of x times the derivative of x, which would be 1, or negative f of x. Now, if you realize this, you probably could have done this and used the rules from 2 lessons ago. Flipped around, it would make a negative, and then it would fit more of the book definition. Alright, there's one more thing in this section that we're going to talk about before we move on, and that is the mean value theorem for integrals. Alright, so the mean value theorem is kind of talking about the average. So if you want to find the average velocity, average of something, and that thing is changing, you can't just add up all the pieces and divide by however many there are, because they're changing at all different things. So think about average velocity. I have a little thing to think about up there, but average velocity is probably a little bit easier. You want to take change in displacement, S final minus position initial, over, let's use B and A. That's a B, position of B minus position of A, over B minus A, right? Okay. But we have things in terms of velocity. We want to find the average velocity. So I'm going to show you what it is, and then we'll talk about why that is what it is. So if you want to find the average velocity, you're going to take the integral of velocity from A to B. And if I was to do this, I'm going to get position at B minus the position at A. It's kind of what we want, but that's just our change in position. Antiderivative velocity is position. We take a final minus initial, so we have S of B minus S of A, but we got to divide it by B minus A. So now we've got to change the position over change in time. So we're missing the over B minus A, so 1 over B minus A has to go out front. That could go underneath, like here, but this is generally our formula for the average value. Now, this is not the average value of displacement. I know the antiderivative of velocity is displacement. This is the average value of velocity. So the average value in general, anytime you want the average of something, f of x dx from A to B, to make it an average, you just put the 1 over B minus A out front. That is the mean value theorem for integrals. Alright, that being said, let's try to do this particular one. So Eric drops his hacky sack from this year's tower. Gravity has an acceleration of that. Find the average velocity of the hacky sack. Okay, so the first thing we got to do is find velocity, which is the integral of our 9.8 meters per second. Okay. And our velocity is going to be just 9.8 t plus c. Okay, well, what's my initial velocity? Drop in a hacky sack, so my initial velocity is 0. So if I plug in t to be 0, my velocity equals 0, So 0 equals 0 plus c, because you're dropping it. That's what tells us the initial velocity is 0. Okay, so what we want to do is our velocity equation. We're going to take the antiderivative. We want the average velocity between 2 and 4 seconds, so 2 to 4. 1 over 4 minus 2, or 2. And let's b minus a, because you want this generally to be a positive number. But you can have it flipped around, and then it would be negative anyway. And we want to have 9.8 t dt. Now there's actually a choice we have to make. And to tell you the truth, you don't actually technically need to make it. Should we have the acceleration velocity, the acceleration of gravity be negative because it's going downwards? Now, I don't care. Think up, down, left, right being positive or negative. But generally, you probably want to make your 9.8 being negative, which doesn't change a whole lot much, but does change that. So we got 1/2 for here times the negative 9.8 t squared over 2. And then you got to plug in your 4 and your 2. And you might be wondering, well, does this half have to come outside of it? It can be outside, it can be inside, it doesn't matter. If you want to put it inside, then that would make it over 4. So, we toss this in the calculator, we get our average speed. So let's do that really quick. So, we have negative 9.8 times 4 squared divided by 4 minus another negative 9.8 times, I'll just do the whole thing. So just writing this as 4, it's 2 squared divided by 4. I understand this is 1. Probably could have done a good deal of that in there. Negative 29.4. So that's our number. Let me read this. This works out to being 29.4. And the question would be, what kind of unit is it? Well, acceleration is in meters per second squared. And velocity is in the distance per time. So it's going to be just meters per second. So your average velocity had better actually be a velocity. And that's the main thing. So if you want an average of your function, do the integral of the function. I know that seems to take it out of being the function, but the 1 over b minus a, that's what makes it the average.